Hello everyone. So after the special relativity topic, we are going to look at the next item in store, which is electrostatic. So I hope you know that matter is made of particles, which are either positively charged, like for example, a proton, right? Or negatively charged, for example, like an electron. Now, some of you might say, well, but aren't there some particles that have no charge, for example, like a neutron? Well, technically speaking, neutron does have a charge, but it's neutral because it has the same amount of positive charge compared to negative charge. So, for example, if you look at like a regular object, a piece of wood, most likely you find that piece of wood to be neutral, but that doesn't mean there's no electron and protons inside. There are just, about the same amount of proton and electron inside. Therefore, the charge is overall neutral, right? When you have positive charge and negative charge and they have approximately the same amount, the object tends to be neutral. Now, what is the unit for charge? You should have learned that earlier in science, but let me remind you, or in case you don't know, charge is measured in coulomb. Okay, coulomb. So this is named after a scientist, of course. That's why it's capitalized. So coulomb. Okay, so we can say I have 1 coulombs of positive charge, or I can have like 60,000 coulombs of negative charge. Right. So the next one, charge, is a lot like mass. Sometimes when you look at the description, charges are always conserved. That means you cannot create or destroy charges. So for example, if you have 10 electrons entering a room, you should have 10 electrons exiting that room at some point. You cannot simply just destroy the charge of an object. Or if you have proton, which is a positive charge, you cannot just put a spell and make the positive charge go away. It will always have that positive charge on it. It's something that comes with the particle. Just like mass, it's very difficult to ask what charge really is because, for example, if I ask you what is mass, like what is 5 kilogram, you say, well, that's the mass of the object. See, you just use the definition of the word to describe itself. Mass and charge are both property of matters. They are a property of particles that comes with the particle. So far, we actually don't know where they come from. We just know that a particle must have some kind of mass and it must have some kind of charge. That's all we know. So, now, another thing is charges are also quantized. Now, that's a new word. What does that mean when I say something is quantized? That means they occur in finite packages. That means you can have 1 coulomb of charge. So there is a smallest unit of charge. So the smallest unit of charge that you can ever find is the charge that is actually on a proton or on an electron. Now that is called elementary charge. So now I'm not saying that you cannot have like 1 coulomb of charge. You can actually have smaller than 1 coulomb of charge. The smallest unit means the smallest amount of charge that you will find on anything, right? So now how much is that? That's the charge of 1 proton or 1 electron. Now, it might be surprising, maybe not, that the charge on protons and electrons are actually exactly the same, except that proton carries a positive type of charge and electron carries a negative type of charge. The symbol for charge in our equations that you will see later on is Q. It's either a big Q or small q, doesn't really matter, capitalized Q or lowercase q. So for example, for a protons or electron, the amount of charge on it is either positive if it's a proton or negative if it's an electron. And the amount is 1.6 times 10 to the negative 19 coulomb. Okay, so the charge of 1 proton is 1.6 times 10 to the negative 19 coulomb. The charge of 1 electron is negative of that value. So they are the same amount, but one is positive, the other one is negative. So electron will have a negative 1.6 times 10 to the negative 19 coulomb. So you won't find a charge amount that's less than that. So for example, an apple can have 2 extra electrons on it. Then how much What is the charge of the apple? Well, if it has 2 extra electrons, it will have double the amount of this 1.6 times 10 to the negative 19 negative on it. Okay, so any object that has charge is either because it has too much proton or too much electron. Any object that is neutral is because it has the same amount of proton compared to the amount of electrons. Okay, sorry, I make a mistake. I said proton and neutron before. Protons and electrons. Okay, so if you have extra electron, you have a negative charge overall. If you have extra proton, you have positive charge overall. Okay, so what does charges actually do? Well, when you have mass, you have gravitational attraction force between the two objects, right? Now it turns out the analogy for charge is actually almost exactly the same. Coulombs determined that the force between two charged objects is proportional to its charge and inversely proportional to the square of the distance. That means if you have two objects with charges, there will be a force in between them. And the force is determined by this equation, K Q1 Q2 over R squared. Okay, K Q1 Q2 over R squared. Now, if you look at this equation and then think about gravity, which is G m1 m2 over R squared, you can see the similarity between the two equations, right? So two objects with mass attract each other. Two objects with charge also sometimes attract each other. Now, the weird thing, though, however, the one extra thing, so first of all, let's define these variables in the equation first. Now, charge, this is a force, so obviously it will have a directions, right? So it's a vector, it has directions. Now, so Q1 is the first charge, the charge of the first object. Q2 is the charge of the second object, which is measured in Coulomb. Okay, so first object, second object. R is the distance between the two objects. Okay, so for example, if you have an electron over here and you have an electron over here, then there is a distance between them, that's R. Okay, and the charge on the electron is, well, that amount, right here, 1.6 times 10 to the negative 19, negative on both of them. Then you have this one extra thing, the last thing that you don't know, which is this K value. Well, just like in gravity, we have a gravitational constant G, which tells you how strong gravity is. Coulomb's force, which is also we call it electrostatic force, right? So this is a electric force or electrostatic force. So electric force. So gravitational force is one of them that we learn, one of the fundamental force. Electric force is another fundamental force in our universe. Now, this electric force is governed by this constant K, which is called the Coulomb's constant. Okay, so named after the scientist again. So this electric force equation is also called Coulomb's law because of that. Now, this Coulomb's constant, just like gravitational constant, is a number. It's a number that you will find on your formula sheet. And it's 9 times 10 to the 9. Okay? And the unit is Newton per, I think it's Newton meter square per Coulomb square. Okay? The unit is not very important in this case. Just the value, right? 9 times 10 to the 9. Okay, now this equation can be found on your formula sheet, but you have to be very careful. If you actually have the formula sheet with you, I want you to take it right now and make some remark on this equation. This equation can only be used for magnitude only. Now, and I want you to add this 2 bar, which is an absolute value. Okay, absolute value. That means don't worry about plus or minus sign for those two charges. Electron, yes, should have a negative charge, but ignore it. Protons should have a positive charge. Okay, so that's positive. So this equation actually cannot tell you direction. So only use this equation for magnitude. That means you get the amount of force between the two objects. And when you want to, so for example, let's say in the example that we have down here, which has 2 electrons. So what we know is that they will repel, right? So 2 negative charge objects will repel. So we can find out how strong is the force repelling them, which is called the electric force. We can use this equation to find it, the Coulomb's law. But that's good enough. We won't be able to tell the direction. I mean, we can tell the direction by drawing the picture. We know that the electron on the left is going to go to the left. The electron on the right-hand side is going to go onto the right-hand side because they're repelling. However, the equation doesn't actually give us directions at all, because positive in this case could mean left or right, right? So if you cannot tell the equation, if you cannot tell the direction from the equation, you might as well not actually put the negative in to confuse yourself. So when we use this equation, the Coulomb's law, we never actually put the plus or minus sign into the equation. Even if the charge is negative, we don't put it in. So just put that remark in here. So this is for magnitude only. So for magnitude only, that means just get the force from this equation and don't worry about direction. Now, I'm not saying that you should not care about the direction. I'm saying that you cannot get it from this equation. So this is for magnitude only. Okay, so for direction, so if you lead the direction, which you will, use diagram. If you use the diagram, draw a diagram like the one that I draw below, you'll be able to tell which way does one of the electron move. You say, if I ask you, hey, which way does the electron on the left move? You say, oh, to the left. Which way does the electron on the right move? Oh, to the right, because they're repelling in this case, right? So don't use the equation for direction, plus or minus sign, drop all of them. Use the diagram for direction. Okay. So now, hey, there's something different between gravity and electric force. Gravity can only attract. Look at these two objects. They actually repelling each other. So these two electrons, right? So gravity can only attract, but electrostatic force can either be attractive. Now, when will it be attractive? It is attractive if you have different charges. For example, like a protons and a electron, then they would like to stay together. So they will be attracted toward each other. Okay? If you have a positive and a negative charge. Or it can be repulsive. Now, when will it be repulsive? Well, it's easy. If you have two protons or two electrons. So, for example, like two positive charge or two negative charge, then the object repel. Okay, so what does electrostatic force depend on? Now look at the diagram. It depends on charge, right? The Q1 and Q2. So it only depends on the charge of the object. Okay, so only depend on charge, and it does not depend on mass. Okay, so it doesn't matter how heavy the object is. The electrostatic force is here because of the amount of charge on it, not the amount of mass on it, right? Mass can get you gravitational force, not electrostatic force. Now, and then you look at this equation again, you see it's going under r squared, right? Dividing by r squared. That means if you increase the distance between the two objects, the force will actually drop very, very fast. Okay, it will drop very, very, very quickly. So the electrostatic force gets significantly smaller or small as r, which is the separating distance, increases. Okay, so when the distance increases, the force gets really small really quickly. The last thing to notice in here is this constant, the Coulomb constant, which is this K value, right? This constant K value right here. So this Coulomb constant K is actually much, much larger than the gravitational constant G. If you don't remember, K is 9 times 10 to the 9, right? Which is 9 billion. G is 6.67 times 10 to the negative 11. It's not even a positive power. It's 0. Then 10 0 later, you have a 6 for the gravitational constant. Whereas for the Coulomb constant, it's 9 times 10 to the 9. Okay? It's very, very different. 9 times 10 to the 9 is actually 90 billion, yeah. Okay? So electrostatic force is usually a lot stronger than gravity. Okay? So, very important difference between gravitational force and electrostatic force is gravity always attracts. I think we already mentioned that. Gravity always attracts, whereas the electrostatic force can either attract, so it could attract, of course, but it can also repel. And then going back to what we were saying before, when we are solving for electrostatic force, we will not use plus or minus signs, right? We will not use plus or minus signs on the charges. Okay, so don't use the plus or minus sign in the equations, just use the diagram. Okay, we can determine the direction of the force on each object based on the fact if they are attractive or repulsive. So based on attraction or repulsion. All right, now let's look at some example at this point. So I'm going to go through 3 easy one and 1 slightly harder one. All right, so to the next page. So first of all, let's confirm what we just said earlier, which is the fact that gravity is a lot weaker than electrostatic force. Let's see if that's actually true. Now we have 2 people standing 1 meters apart, 85 kilogram each. What is the gravitational force between them? Now remember, G is 6.67 times 10 to the negative 11. That's the constant. And 2 person, each of them 85 kilograms, so 85, right? And then you divide by their distance square, which is 1 meters apart. So you say 1 and then square. Now, you crunch that in your calculator, and you're going to get a force that is 4.8 times 10 to the negative 7. So 1 in like, it's like 5 in 10 millions of a Newton. So it's not even 1 Newton, right? It's 0.0000005 Newton approximately. That's the amount of gravitational attraction between the 2 people. Now, but let's say these 2 students each have a charge of about 2 times 10 to the negative 3 coulomb. What is the electrostatic force in between them? Okay, so now electrostatic force, we have K Q1 Q2 over R squared. K is the Coulomb constant, 9 times 10 to the 9. This, again, is the Coulomb constant. Okay, and then we need the charge of the 2 objects. Now this is just 0.002, I believe. 1, 2, 3. Yeah, 0.02. So it's 0.002 Coulomb twice, because both objects have that charge. And then divided by the distance, same distance, assuming same distance square. So now try doing this on your calculator. Use the result. That is 36,000 Newton. Now, notice that we didn't actually put any plus or minus sign onto our equation with the charge, because we don't need it. Now, if these 2 students have the same amount of charge, so this is student 1, this is student 2, and they're separated by 1 meters apart, right? 1 meter, and they're both positive charge. Now, why do I say they're both positive? If you look at the charge, it's 2 times 10 to the negative 3. Positive 2 times 10 to the negative 3, right? It didn't put negative in front. So which direction would the force be pointing at then? If you have the same charge, the 2 objects will repel. So this is a force that repel. So for direction, I don't know if you want to know the direction for which person, right? You have to tell me if you want the exact force. So of each person, then it's going to be 36,000 Newton to the right or to the left, depends on which person you're concerning about. So it's exactly the same amount. For the person on the right is going to the right, for the person on the left is going to the left. It's 30,000 either on the right or to the left, depending on which person you actually concern yourself about. Okay, so pretty quick. Let's do another one. 2-point charge. Now, point charge is an object, like a proton and electron. So 2 small objects with 2 charges produce a force of 2.2 times 10 to the negative 3 Newton. Now, I do have to warn you about one thing. Charges are usually very small. Like, think about it. A proton or a electron, right? If you look back, has a charge that is like 10 to the negative 19 Coulomb. So a lot of time they will use For example, they will use micro to actually in place of this. So this is also called microcoulomb. It's like kilometer is one of those p-fracs. Micro means 1 in a million. So when you have 10 to the power -6, that means in a million. So you might see some questions on the worksheet or in the future writing that 1.8 times 10 to the -6 coulomb like this, 1.6 microcoulomb. So in this case, micro means times 10 to the -6, right? Okay, so 1.8 microcoulomb, 2.6 microcoulomb produce a force of 2.2 millinewton. How far apart are these two charges? Okay, so we are looking for distance between them. So the force is given, which is good. So we put the force in here, 2.2 times 10 to the -3. So that's just 0.0022, right? Why would they have to do that? Okay, so now I have this, then Coulomb constant, 9 times 10 to the 9, and then the two charges, right? Now the two charges are not the same this time, not anymore. So one of the charge is 1.8 times 10 to the -6. The other charge is 2.4 times 10 to the -6 coulombs, right? I'm lazy, not writing the unit. I should have. And then r square. So what we're looking for is the distance in between them square. Okay, so I mean, you're in grade 12. Do I really have to go over the algebra, right? So if you are looking for some hints, you should swap the 0.22 and the r square. You can just swap them and you can do all the calculation on the right first, and then r squared equal to that number. Take a square root on both sides. Then you get the separating distance between the two charges. So the separating distance, rounding to 2 sig figs, is about 4.2 meters. So again, an easy one. You have all the information but one thing, just plug it in. All right, now this next one is going to be a bit more challenging. So we're going to move on to this. So now we have three charges, multiple charge. So a charge of 1.7 times 10 to the -6, so 1.7 microcoulomb, right? 1.7 microcoulomb, which is this one right here, is placed this 2 times 10 to the -2 meters from a charge that is 2.5 times 10 to the -6 microcoulomb. Now, first of all, what on earth? This is just 0.02, right? Okay, and what is that distance? It's the distance between this one and this one, right? 0.02 meter. Okay, now we're going to name them. We're going to lose track on them very, very quickly if we don't name them. Let's go with 1 and 2 and 3. So from now on, we're going to call them charge 1, charge 2, charge 3. So this is going to be like Q1, the charge on the first one, right? Q2, the charge on the second one, right? And Q3, the charge on the third one, right? So we're going to call them that from now on. All right. Let's go on. And okay, so it's 0.02 meters from a charge of that, and it's 3. Okay, so that's another piece of information. It's 3.5 times -2 meters from the charge of -2 times 10 to the -6. So the first two charges right here is actually positive. 1 and 2 is positive, and 3 is negative. Okay, so there is a positive charge and a positive charge and a negative charge. Okay, so like that. Now, what is that distance? This is 3.5 times 10 to the -2. That's 0.035. Where is it? It's from the first charge to the second charge. You have to read this thing really carefully. Oops. Accidentally touched the screen in the wrong corner, and that happens. Okay, there we go. So this is 0.035 meter all the way from charge 1 to charge 3. All right. Okay. So there we go. So that's a negative charge. That's positive. Okay. So what is the net force on the 1.7? Okay, so on charge 1. What is the net force on charge 1? Okay, so first of all, remember net force? That means all the forces combined. Net electric force on charge 1. Okay, so we want the force on charge 1 only. So what we have to do is cover up the charges and only look at them one at a time. So for example, first, let's look at only charge 1 and 2. Now, if you only look at charge 1 and 2, it will be like this picture, right? You only look at charge 1 and 2. Now, between charge 1 and 2, which direction is the force between them? Well, I will give you this picture. Hopefully it makes sense, right? Between charge 1 and 2. Charge 1 and charge 2 are both positive, so they should be repelling. So therefore, we have a force between charge 1 and charge 2. Right there. Now, how strong is that force? Well, this force is going to be between charge 1 and charge 2. So I'm going to call it force 1, 2. The force between 1 and 2, right? Force 1, 2. Now, I only care about the force on charge 1, as the question asks, right? Let force on the charge 1 only. So I only care about the force on this guy. I don't care about the force on the charge 2, so I'm going to erase that one. I don't care about that. Okay, cool. So we have a force 1, 2 pointing to the left. Okay, now the legs part is going to be a little bit more complicated because I'm not in front of you right now to actually cover up something. But what I need you to do is actually mentally, or maybe not mentally, I'll just block it with some color. We are not looking at charge 2 anymore. Consider that gone. Now we are only looking at charge 1 and 3. Why 1 and 3? Because I want a total force on charge 1. So there is an interaction between 1 and 2, and there is an interaction between 1 and 3. Well, you say, Mr. Chang, what about the force between 2 and 3? Oh, I don't care. I don't care, not because the force is not there. I don't care because the question is asking you, what is the force on 1? So I don't care about the relationship between 2 and 3. I care about the relationship between 1 and 2 and the relationship between 1 and 3. So now you look at 1 and 3. 1 is a giant positive charge, 3 is a giant negative charge. So therefore, what kind of force is between them? Well, I hope you are answering that in your head right now. Attractive force, right? When you have a positive and negative charge, they attract each other. So what happened is there is a force right here, attracting charge 1 and charge 3 toward each other. Now this force is going to be named force 1, 3. Why 1, 3 is the force between 1 and 3. It's exactly the same amount on the other side with the charge 3, but do I care about that one though? I don't, because the question is asking me for, again, one more time, the net force on charge 1 only. So I don't care about this one. The one on the charge 3, I don't care about it. Okay, so now here's the picture. So let me make charge 2 come back. Charge 2 is back. So I care about charge 1, and there are 2 forces on charge 1. It's like tug of war, but you're being pulled on 2 sides by 2 different people. First, there is a force from charge 2 pushing you away. So it's like someone pushing you to the left, and that is all due to charge 2. Then there is a force that is pulling you to the right hand side, you being charge 1, right? And that is due to charge 3. Charge 3 is trying to attract you over there. Okay, so charge 2 is pushing you, charge 1 is pulling you. Okay, and those 2 forces are fighting each other. All right, that is the difficult concept because you have to look at the 2 charges separately. So imagine that you are, you are charge 1. There are just basically 2 forces acting on you right now. Okay, so now let's do those 2 forces separately. So between 1 and 2, we did charge 1 and charge 2, right? So that will be K. Now I'm going to, maybe this is like the first class, so I'll actually write K multiple times. I'm going to stop writing K starting next time. Okay, just like I never write the gravitational constant because I assume that everyone should know. So this is the Coulomb constant. Charge 1. Charge 1 is 1.7 times 10 to the negative 6, 1.7 microcoulomb. Charge 2. Charge 2 is 2.5 times 10 to the negative 6. Okay, so I have K, Q1, Q2. Now they're all positive, so I don't have to worry about anything. The distance between them, okay, so that is a number I need. That is 0.02 meters. Make sure I square that. Okay, so now this will give us the purple force, right? The F12, the purple force. Now the purple force turns out to be about approximately 96. Okay, approximately 96 Newton. 96 Newton, approximately. Which direction does it point toward? Look at the arrow on charge 1. That is going in which direction? That is going to the left, right? So this is to the left. So now we do the next one. Now the next force is this orange one. So force 1, 3. This is the orange one, which is pointing to the right-hand side. So to find that force, we need to change the equation a tiny bit. Not a lot, just change it like a little bit. So it's K charge 1 charge 3 over R squared. Now this R is not the same as the other R. These two are not the same thing. The first one is the distance between 1 and 2. This one is the distance between 1 and 3. Okay, so there we go. So probably need to be that long. There. Okay, so 9 times 10 to the 9, that's Coulomb's constant. And then we have the charge 1, which is 1.7 times 10 to the negative 6. And then we have charge 2, which is 2 times 10 to the negative, this is charge 3. But notice here, charge 3 is actually negative. But when we put it on the equation, we don't put the negative sign. Okay? Do not put that negative sign there. Okay? Remember, we kind of have an absolute value on this whole thing. So even if you did put the negative sign, the negative sign should be destroyed. Okay, so don't put the negative sign in. We know which direction that force is pointing at. Look at the orange arrow. Which direction is it pointing at? It's pointing to the right, right? We don't need this equation to tell us which way it's pointing. Okay, we have a picture. The picture is telling us which way it's pointing. We have a picture up there. Okay, so now we are going to divide by. Now, the distance between them is 0.035. So we divide by 0.035 and that square. Okay, all right. Now, and this is the orange force. Let's use orange. So how much would that be? So in a calculator, this is approximately 25 Newton. And for direction, which way does that point? This points to the right-hand side. Okay, so what is the total force on charge 1? Now, you have a 96 Newton force going to the left, a 25 Newton force going to the right. So therefore, you sum it together and you have your final result. The net force, okay, so the net force on charge 1 is equal to the difference between these two. Now, because they're one going to the left, one going to the right, so you would say 71 Newton after you subtract them. So approximately 71 Newton. And you don't have to put a sign. Just say 71 Newton and then which way. Now, this is a tug of war, right? So the one on the left is winning because it's bigger. So therefore, to the left. So 71 Newton to the left. And then that's it. Okay, so there we go. Now, for homework this week, there is actually a worksheet attached to the end of this. I will have another video posted to talk about one of the questions on that worksheet. Let me show you which one, but I'll put it on a separate video because it's not part of the note. So if you look at this is the worksheet 6.1. I'm not asking you to do all the questions. I'll ask you to, I'll put all the information on the course webpage, of course, discussing. But I would have a separate video dealing with this question 8, where the 3 charges, as you can see right now, is not on a line. So you have to deal with some angle and, you know, a little bit of those vector thing that we have done so many times earlier. Okay, basically what happened is that you will have 2 forces and but they won't be something that you can directly add or subtract because they're on a different angle, right? So if the 2 forces are on a straight line, you can actually add them or subtract them. But if they are not, then unfortunately you will have to use a little bit of trick. I'll post it on a separate video. Okay, goodbye everyone and have a nice week.